Discuss about support vector machines. We have already covered support vector machines in the past, so we will just fill in the couple of two. There are two critical questions which we haven't answered, which we will discuss about now. First is, what if there's noise in the data and no hyperplane can perfectly separate positive examples from negative ones? And secondly, what if the data cannot be separated using a plane but could be separated by a higher order polynomial? So remember that in SVM we are trying to get these uh, constraints satisfied, right? We want, in case we want a line, we want our two categories y to be, one should be defined as 1 as -1, and for if our y is 1, then our wx minus b should be either greater than or equal to +1, so that it's either on our margin or after it, right? Same for the negatives, right? And we also want to minimize our we want to make sure that our hyperplane is equally distant from the closest examples of each class, right? So for example, if we built a hyperplane here, these closest examples will be called support vectors, and we want it such that our decision boundary is maintaining the maximum margin between these support vectors, right? Now here you can see there is, at the left side there is noise present, and in this blue data points you can see there are two red, in the red there are two blue, and in the right you can see there is an inherently non-linear data. So in what do you call it? In support vector machines, we are trying to solve this optimization problem. We want the distance between the nearest support vectors and the margin to be at least half, right? Such that, yeah, so we simply want that the distance from both should be equal, right? So half distance here, half distance here. It tilted to any side will result into more of a problem. And in data where your in examples where your data is not linearly separable, we introduce the hinge loss function. So what the hinge loss function does is it takes the max, right? So it takes 0. So if all your constraints are satisfied, right, if it's on the right side of the decision boundary beyond the margin, it will take 0. Otherwise it will take 1 minus your prediction. So it's simple, right? You are trying to minimize the following cost function. There is a max, it will take either of 0 or either of 1 minus y, which is simply your 1 minus your y predicted, which is simply your wx minus b. And so it takes the maximum value. So if your error is present, it will be taken, otherwise your error will be 0, right? So it doesn't the distance from the line does not matter. What matters is if it is correctly classified. Then it sums these up, divides it by the number of total records, and that is how this is the hinge loss function, right? Here this hyperparameter c will decide whether it wants to increase the size of the decision boundary margin and ensure that each x lies on the correct side of the decision boundary. So simply c is a hyperparameter which will decide whether you want to increase your margin or decrease it, and it is usually chosen experimentally, just like the ID3 parameters before. SVMs that optimize hinge loss, which is simply this loss function, are called soft margin SVMs, while the original formulation is referred to as hard margin SVM. Nowadays mostly soft margin SVMs are used. So C simply tries to maintain that our model is classifying the training data well, but should also be capable of classifying future examples well. So it does this by maintaining the margin in a way where it is not overfitting, but it shouldn't be underfitting either. Because if we make our c value very high, this entire second term of the cost function will become very negligible, right? While if we keep it very low, our errors will become our errors, making these errors will become very costly because they will start to affect the performance of the model more strongly, right? Suppose you had this type of data, right? This second example. So how do you separate this type of data using SVM? Like, no plane can exactly separate it. So we do this by introducing a higher dimensional space, and this is done using something known as the kernel trick. Kernel trick will simply convert this two-dimensional data into a three-dimensional space. So what it says is it takes some points q and p and it multiplies them by each other, right? So it computes the relationship between any 2 points in a higher dimensional space, so it squares them. So what happens is, here you have these two axes, and then it will create a third axis, and this third axis will simply be your x-axis into y-axis squared. So it will be like -10, so -100, -25, 0, 25, 100, right? And what will happen is, you can see here it's same, right? 0 to 120 the values are spanning, and no, wait a second. Yeah, so simply because of this, you got a third dimension, right? See, you can see here it's taking points q and p, and through that is getting q squared, root 2 qp and p squared, right? So because of this third dimension introduced by squaring and creating a new what do you call it, axis, you are able to linearly separate the data. So, but we of course cannot transform all our input examples, right, into very high dimensional vectors. So because if you actually took every variable and computed the higher dimension relationship between every two variables, you would end up with a huge computation. Like, data normally has 10,000, 20,000, more than that records, sometimes millions. And if you try to compute the higher dimension, that means if you try to square every 2 points and get their relation, you're going to end up with a humongous computational problem. So there's something called the kernel trick, which will calculate the higher dimensional relationship without actually transforming this 2D data into 3D. So we will cover this in, yeah. So what it uses something called Lagrange multipliers to achieve this. I will not be going into that exactly, but just so that we know, it uses something called Lagrange multipliers. Right, and then it uses something called an Euclidean distance to find the distance between two feature vectors. Euclidean distance is simply the Pythagorean theorem which it uses, right, to find the distance between the data points. And so what it does is simply says, okay, distance between this and this would be like, it will take this y-axis and this x-axis, and then use that to compute this distance. I will explain it further if we get a better chart ahead. Okay. And next we have k nearest neighbors. K nearest neighbors is a non-parametric learning algorithm. So it does not, so it's an instance based learning algorithm. As I said before, it will not discard the training data after the model is built. It will keep the training data in memory, because by using the training data, what it's going to do is, once it gets a new example, it will find a k, which is some number of training examples closest to k, and whichever label is in the majority in those examples, it will be classified as that label, the average label. In case of regression, in case of classification, it will be the majority label, right? Because in regression you have continuous values, in classification you have a set of categories. again here you can see that for Euclidean distance is most often used, right? Another is like negative cosine similarity. Euclidean distance is simply like Pythagoras theorem, right? So what it does is it says in this example it will try to find the distance between, you can see, this point and this point, and to do that what it does is simply connects a line from this point to the x-axis and this point to the y-axis, right? So what this will do is these two lines will intersect and this will create a right angled triangle, and then by using the value of this line and this line we can calculate using Pythagoras theorem the distance between these two data points, and we can do the same for every data point, right? Like the distance between this, the what do we call it, the Euclidean distance between this and this data point will be almost negligible because they're literally on the same point, but for others it will be higher, right? Another thing, cosine similarity simply takes the angle between two vectors, right? So it will join a line here and find what is the angle, right? Because if the angle is 0, like in this case the angle is 0, right? So your x features which are using to predict your y feature, so your y feature doesn't matter, your x features are almost similar, right? Because your angle from all direct is like literally 0. But if you have like a data point here and a data point here, you can clearly see there is like a 60 to 70 degree angle, and that means both the data points are not pointing at the same direction, and thus there is a distance. Now we will discuss about the anatomy of a learning algorithm. Every learning algorithm has some common criteria, some blocks. Firstly, every learning algorithm has a loss function, an optimization criteria based on the loss function, and an optimization routine. So simply it will have an error calculator, an optimization criteria which tries to understand the loss function, and another optimization function which will try to adjust the values to find the perfect fit for our equation. Now you will often hear about gradient descent and stochastic gradient descent, which we will cover, right? Gradient descent is used to find optimal parameters for linear and logistic regression. Even SVM and neural networks use it. So let's see how gradient descent works. For example, you have this chart which shows you the sales in units and the spendings in millions of a radio, I think it's a radio company. So we have, yeah, it's about radio ads in relation to sales in units, right? So here is our data set, for example. So we have these different companies, their spendings in radio advertisement and their sales in units, and this is their 2D plot. Now a linear regression model will have a line, and the equation of a line, which in our case is function of x, will be equal to wx plus b. Now we know x because x is simply our spendings in million. That's our independent variable, or our feature variable, and y, which we are trying to predict, which is f of x, will try to predict is our sales in units, which is our target variable. So we don't know what w and b, which is our weight or our slope and our intercept, will be, and we want to learn this from the data. So to do that, we will look for values for w and b that minimize the mean squared error. As I explained before, this is how the mean squared error is calculated. It takes the actual value of y, subtracts it from the predicted value, squares it so that the negative values don't cancel out the positive, adds them all up, and takes the mean, the average, by dividing it by the total number of data points. Gradient descent starts with calculating the partial derivative for every parameter. So simply it's trying to find out how much a change in the weight is affecting the change in loss. By how much will I change the weight? So if I change the weight by 1, how much is the loss going to change? And it uses this derivative to calculate that. So simply it took this squared, and because this is this is we're taking derivative, so as I explained before, x squared turns into 2x, so this became 2x, and x came outside. We will go into the derivative part in the neural network section, but for now this is how it calculates the partial derivative for both intercept and weight, right? So to find the partial derivative of this term with respect to our weight, we apply something known as the chain rule, right? So chain rule here is our f1 is this y minus wx plus b, and to find our partial derivative of f with respect to w, we first need to find the partial derivative of f with respect to f2, right? So this will be equal to 2y. So simply, what is the derivative of this? Just this much. So this, the derivative of this will be 2, and the bracket, the stuff in the bracket remains the same. So square turns into 2, and then yi minus wx plus b. Because we know, see, it has mentioned here the derivative of x squared in relation to x is 2x, right? And then we have to multiply it by the partial derivative of yi minus wx plus b with respect to w, right? And here we are taking b as a constant because we are taking a partial derivative, so b becomes 0, y is also a constant, so it also gets eliminated, w becomes 1 since it's a coefficient, and x remains as x, so minus x. So overall it turns into this minus 2 into yi minus wx plus b into minus x. So this becomes minus 2x into yi minus wxi plus b. So in this way we calculate the partial derivative for weight and bias. Now gradient descent proceeds in epochs, right? An epoch consists of using the training set entirely to update each parameter. So in the beginning we will initialize some random values, so we give weight value 0 and bias value 0, and the partial derivatives we will at each epoch we will update our w and b, which is currently 0, by using the partial derivatives, and the learning rate will control by how much size we want to update. So we will simply subtract the partial derivative, but we don't want to end up taking a, we don't want to end up subtracting too much, so that's why we're using a learning rate to keep things in control, because this is going to grow as the values of as the values of w increase. This partial derivative will also grow, so we don't want that over time we are taking too large steps and we miss the lowest point of error.